welcome to Zassenhaus series 2019. This year we have Pavel Etingof from MIT, who's here to Wednesday. Most of you know more about Pavel than I do, so I'm going to keep this very short. I'll tell you what Etingof said about Pasha about 6 years ago at Northeastern University, Boston. And he said, you see, I'm from New York, and New York is very different from Boston. When we have to learn something, we have to read a book. Here, you just go and ask Pasha. I guess I can't make that more perfect, so I'll just let Pasha tell us about representation theory without vector spaces.
Okay, thank you very much. It's a great honor and pleasure for me to deliver Zassenhaus Lectures here in Ohio State and to see many familiar people. So I should say that, for example, Jim Cogdell I met 30 years ago almost when I was at Yale, a graduate student, and he was visiting Petetsky Shapiro. And Professor Friedman I have not met at that time, but I read his papers on applied mathematics 35 years ago when I was writing my master's thesis, because I have an undergraduate degree in applied mathematics. Yes, and so my topic is algebra and representation theory without vector spaces. So I will try to convince you that in representation theory, when we start with representations of groups on vector spaces, actually we have to move on to representation theory without groups, replacing, for example, groups like quantum groups, which are not groups. And what is worse, sometimes we have to even give up vector spaces and pass to tensor categories. So this is what the lectures will be about. And in this regard, I want to quote something that serves as an epigraph for our book with Gilaki, Nikšić, and Ostric on tensor categories. So several people here read this book and they know this, but I will read this. So this is a short story by famous Russian absurdist poet Daniel Harms, written in 1937. And the story goes like this in English translation. There was a red-haired man who had no eyes or ears. Neither did he have any hair, so he was called red-haired by convention. He couldn't speak since he didn't have a mouth. Neither did he have a nose. He didn't even have any arms or legs. He had no stomach, and he had no back, and he had no spine, and he had no innards whatsoever. He had nothing at all. Therefore, there is no knowing whom we are even talking about. It's really better that we don't talk about him anymore. And there is a footnote which says the following in this book. Philosophically, the theory of tensor categories may perhaps be thought of as a theory of vector spaces or group representations without vectors, similarly to how ordinary category theory may be thought of as a theory of sets without elements. As seen from the epigraph, this idea, as well as its dismissal as abstract nonsense, common in early years of category theory, were discussed in Russian absurdist literature several years before the foundational papers of MacLean and Eilenberg on category theory, 1942-1945. So, and with this, I want to start talking about algebra and representation theory without vector spaces, which is very much in this spirit. So should probably start here. So suppose G is a group. And K a field, which I will always assume algebraically closed today. But I will not impose any conditions on its characteristic. I will consider both characteristic 0, in which case you can think of complex numbers, or characteristic P, in which case you can think about algebraic closure of a finite field. So in this case, we can consider the category rep K of G, the category of finite dimensional representations of G over K. So this just means actions of G on finite dimensional vector space. And this is the kind of more modern point of view on representation theory, that we should not study individual representations of groups as people did in old times. Even older times, they didn't even consider representations, but they considered only characters of those representations. But we should consider not even individual representations, but the whole category. So which contains all these representations together with maps between them that preserve the action of the group, called intertwining operators or homomorphisms. So, so this is a very nice and rich category, and I would like to list its properties and structures. So what kind of structures does this category have? And so here are these structure. So first of all, it is K linear abelian. So K linear just means that morphisms between objects form a vector space over K, and the composition of morphisms from X to Y and Y to Z is a bilinear operation with respect to both factors. And abelian means that it, roughly speaking, looks like category of modules over a K algebra. Well, it's not quite true, but it's true that it's always a full subcategory of such a category. So this is Michels' theorem. Although the good definition of this doesn't mention any algebras and is more abstract. So that's one structure. And another thing, it's a property, it's Artinian. So Artinian means that it has two kinds of properties. So the objects have finite length, and morphism space, and for any X and Y, the space hom from X to Y is finite dimensional. I probably should explain what morphisms in this category is. Hom from X to Y, it is the set of all linear maps A from X to Y, such that G equals to GA for any G and G. So it commutes with the action of the group. So these are two properties or structures. And then another thing, and so this incorporates the fact that if you have a representation, then it can have sub-representation, quotient representations. And if you have a homomorphism, you can take its kernel, image, or co-kernel. And composition series for a finite dimensional representation is finite. This is what this kind of stuff encodes. And then the next thing, this category is monoidal, which encodes the fact that we can tensor representations with each other. So if we have two representations, X and Y, then we can attach to it a tensor product, X tensored with Y. So the action of a group element on this tensor product is just action on X tensored with action on Y. And this satisfies some associativity relations. So it's not going to matter much what the precise axiomatics is, but we have associativity. So if you tensor it this way and tensor it this way, then it is the same. But of course, in category theory, we're not supposed to say that things are the same. but we're supposed to give an isomorphism between them, which is called the associativity isomorphism, A, X, Y, Z. It is supposed to be functorial with respect to X, Y, and Z, which means it should commute with various maps from X to X prime, Y to Y prime, and Z to Z prime. And also, it should satisfy the pentagon equation. So let me explain what that is. So this means that if we start off with this bracketing, and we want to reorder the brackets so they are all moved completely to the right. So this means X cross Y cross Z cross T. Then there are actually two ways to do it. So one way to do it is you switch the brackets here. So X cross Y cross Z cross T. Then you switch these brackets here. So this goes to X cross Y cross Z cross T here. And another way is we switch these brackets to ZT. So this is going to give us X cross Y cross Z cross T. And then go this way. And Pentagon says that it doesn't matter which way we go, this way or that way. So there are 5 angles for this diagram. That's why it's called Pentagon. And I maybe should write down the maps so it's clear what they are. So here we are moving this bracket here. So this is A, X tensor Y, Z, T. And here we're moving this bracket here. So this is A, X, Y, Z tensor T. And so here we are moving this bracket here. So this is A, X, Y tensor Z, T. And here we move this here. Right. Oh, I'm sorry. Identity tensor A, Y, Z, T. And this is A, X, Y tensor Z, T. And this is A, X, Y, Z tensor identity. Okay, and so this diagram should commute. So, so this is what is Pentagon relation. And there is also there is a unit object, which is like 1, denoted like this bold 1, and it has the property that 1 tensor x equals x tensor 1 equals x. So there are some unit axioms which I'm not going to spell out. They're very easy to work out. There is just one thing that you can write. So basically, unit object axiomatically is just an object tensoring with which on the left and on the right is an autoequivalence, and also it should 1 tensor 1 should be isomorphic to 1. Okay, then the next, so this is what monoidal structure is. And also it is a symmetric structure. So that means, maybe I should mention that this is just the, 1 is just the trivial representation, which is a representation on a one-dimensional vector space such that the group acts trivially. Then it is also symmetric, there is also symmetric structure, which is there is also symmetric structure which is a possibility to permute the factors c, x, y. Okay, so this associativity is kind of trivial because for vector spaces we really don't distinguish product in this order from product in that order. Similarly we have this kind of structure, and what kind of properties is it supposed to satisfy? So there are hexagon relations. Again, they have to do with what happens if you have a product of three things. So suppose I want to switch this. And maybe I should say that when you have this pentagon, this means that the bracket position does not matter. So more or less it means that you can safely ignore the position of the brackets and everything will be okay. And so then I'm not going to write any brackets from now on. So therefore there is suppose we want to reorder, so we want to switch x tensor y with z. So one way to do it is just do it directly, go to z cross x cross y, and this is c x tensor y with z. But another way to do it is do it in two steps. So first switch y with z and then switch x with z. So when we switch y with z, we take 1 x tensor c y z, and that takes us to x tensor z tensor y. And now we can switch x and z. So this is going to be cx z tensor 1, and then we end up here. And this has to be commutative. And there is a symmetrical diagram, so in the situation that I will consider, so if there is a symmetrical diagram which you obtain when you reflect this in the mirror, and if you impose both of these, this is called a braiding. So this is supposed to be an isomorphism as well as this. Supposed to be an isomorphism. So if we impose two such diagrams, we get a notion of braiding, but I want symmetric braiding, which is that cxy composed with cyx equals to the identity. So if I do this flip twice, I get back what I had. And in this case, the two, if you impose this, then this and its mirror image are equivalent.
Is this a hexagon?
Yes.
Is it triangle?
It's a hexagon because I ignored the brackets. If I didn't ignore the brackets, there would also be three operations that I have to do when I have to move the brackets from left to right, and there would be a hexagon. And so this is like kind of additive structure, which is responsible for things like sub-modules, quotient modules, direct sums, and so on. This is multiplicative structure, which is responsible for tensor products. And then we also have to, when you put two structures on a set or a category, in order to have a sensible theory, you always have to have some kind of distributivity axiom which connects them. That's exactly what is done by the next condition, which says that tensor product. Maybe I forgot to say there is something else about this multiplicative structure that you have to say. There is a operation. There is a third important operation. So there is direct sum, there is tensor product, but there is a third important operation which is taking the dual of a representation. So x goes to x dual, dual representation. So the action on the dual vector space, and this structure satisfies the following conditions. So we have a map x to x tensor x dual tensor x, and I'm putting brackets here because I mean that x goes to this x, and here we have a canonical element. But then you can switch brackets like this. and then you here you can take the inner product and get back to X, and this is supposed to be the identity map. And the same diagram and you need the same diagram for X dual, so I'm not going to draw it. So this is called rigid structure. Rigidity property. So it turns out that if this operation exists, it is unique. It's uniquely determined, and so a category that carries this structure is called rigid. And then you are supposed to have a structure that connects the two, multiplicative and additive. And so this is the axiom that tensor product of morphisms is bilinear. So this is a distributivity, like A times B plus C equals to AB plus AC. And there is a small axiom that I want to add, that endomorphism of the identity is equal to K. So this means that identity object, unit object, is indecomposable. So that's all. So sorry about this abstract nonsense, but this is the structures that and properties that the category of representations of a group has. And a definition that one makes is that a category C, such a category C, is called a symmetric tensor category. So over the field K. So instead of studying representations of groups, we can study more generally such categories and see how much more general it gets. So that's the main question I want to address. How much more general is symmetric tensor category? So I will write this STC then representations of a group. So any questions up to this point? Okay, so well, you can generalize a little bit. So generalization. Well, you can take G to be an algebraic group. And consider its algebraic representations, or more generally, pro-algebraic group which is a inverse limit of algebraic groups. And actually, you can go even more general and say that you are going to take something that is called affine group scheme. Which I can also call G. So what does it mean that you have a affine group scheme? Affine group scheme just means that you have a commutative Hopf algebra. Commutative Hopf algebra of regular functions on G. And let me call it H. And G is just a spec H. So if you want to think about it as a group, You can think of it as like always about any scheme as a functor from the category of commutative algebras to the category of groups. For every algebra A, it assigns the set of maps. So for every commutative algebra A, if you take home as algebras from O of G to A equals to G of A is a group. So this functor which sends A to G of A is the functor represented by this group scheme. And so there is a notion of a representation of this. So a representation of G is a comodule over O of G. So comodule over O of G is basically the same thing as a module over the dual algebra with some continuity property, but it really means that you have some finite dimensional space V together with a coaction, and it should be co-associative. And so we can look at the category of representations of this affine group scheme. And why is it a generalization? Because for every group, it is a generalization of the previous setting, since for every abstract group G, there exists a affine group scheme G hat, which is called the pro-algebraic completion of G, with the property that such that representations of G is the same thing as representations of G hat. Actually, I don't need to write K here because G is a scheme over K, so this is an algebra over K, so we only have the notion of representations over K here. So what is this G hat? So O of G hat is the set of all functions from G to K, which are of the form, so it's a subalgebra generated by my matrix elements of representation. So it's subalgebra generated by things like F, G, V, where V is in representation V, F is in the dual space, where V is in rep KG. So you take a finite dimensional representation, take a vector, take a covector, and then you make such a function on the group, which is called a matrix element. And if you take the subalgebra which is generated by those, it turns out to be a Hopf algebra, and its comodules are exactly representations of G. So that's a standard story from algebraic geometry, or algebraic groups. Generalization of this, and this also includes representations of Lie algebras and of the abstract groups, as I just explained. And the question that we might ask, we're going to keep asking today, is that it? Which means, are there other categories, symmetric tensor categories, than this? Okay, so I'm going to disclose the answer. The answer is no. And now I'm going to stop for questions. Well, eventually the answer will be yes, but you have to wait. So questions? Okay, so no, there is actually a very simple example that doesn't fall into this category. And this is the category of supervector spaces.
The answer is yes.
Huh? What?
No is the answer to the first one. No is the answer to the first question. Yes is the answer.
Okay. Maybe.
You can't be wrong.
So now the answer is yes.
Okay.
It's the wrong question.
Yes. There is a C equals to supervector spaces. So what are supervector spaces? Supervector spaces are so ordinary vector spaces, finite dimensional vector spaces, but graded by the group Z mod 2. So we have V equals to V0 plus V1. This is the even part, and this is the odd part. And by the way, I should say that in order to build supervector spaces, in order for them to be interesting, I need characteristic of K not equal to. And the reason I need that is because, so everything is going to be the same as in usual vector spaces graded by Z mod 2, except the commutativity map. So Cxy from x tensor y to y tensor x will have would be given by the following formula. So if I want to interchange two vectors, this is going to be y tensor x, but sometimes I'm going to have a sign. -1 to the degree of x times the degree of y, when x and y are homogeneous. So which means they lie either here or here. So that means that the only case when it actually differs from the usual rule is when both of them are odd. So if you have two odd vectors, when you switch them, you change the sign. And this is, of course, very familiar. There are differential forms, cohomology classes, so all kinds of things in various areas of mathematics that satisfy this so-called Kazul sign rule. And this category is not of this form. To see this, it's very easy to see. So one way of seeing it is to define the notion of dimension of an object. Well, dimension of an object. So maybe I should. I did not spell out here this duality story. So the duality means that we should have two maps from the unit object to x tensor x dual, which is the canonical element of the co-evaluation maps, and evaluation map, which is the map the other way, which is just the inner product, which satisfy this axiom. So here I should write 1 tensored with the co-evaluation map, and here evaluation map tensor 1. So we're supposed to have these maps, and now if you have both of these maps, you can compose them. So you can go from 1, then go from x tensor x dual. And I should mention that if you have such a thing, and you have a symmetrical braiding C, then this implies that the double dual is equal to x, canonically. So you can go this way, and then you can go back to 1. So this is co-evaluation, and this is evaluation. And composition of this is a map from 1 to 1, but we have an axiom that this is endomorphisms of 1 is k. So this means that this is just a number, and this number is called the dimension of x. And that's a number in the ground field k. So dimension of x is in k. And now, so for example, suppose we have a field of characteristic 0, such as complex numbers, then we can calculate this dimension. So for representations of the group, the dimension will be, so if V is a representation over K, or representations of some group scheme G, then dimension of V. Well, this will be just the usual maps. This is why is it called dimension, by the way? Because so if I compute this map, what happens? So I send. So this is the trivial representation, which is my field K. So under this map, 1 maps to some basis, with some basis xi, tensored with the dual basis xi dual, and then when I evaluate, and this is from I from 1 to the dimension of V. And then when I evaluate, this is going to go to sum from I1 to dimension of V, inner product of xi with xi dual, which is 1. And so this is sum of 1s from I to dimension of V. So this is equal to the dimension of V, or dimension of X, if you like. Dimension of X. So that's why in the category of representation of an ordinary group or group scheme, this is the usual dimension, except that it is regarded as an element of the ground field K. But if V is in supervector spaces, then if you compute this dimension, because of this sign, what you will get is that so the point is that I should maybe I should correct this diagram slightly. There is a step that I missed. So you have to switch x star and x, and this is C, and then you evaluate. So that's the correct definition. And when you do the switching, that's exactly where the sign pops out. And then what it does, these inner products for the odd vectors will come with a minus sign. So what you will get is the dimension of V is dimension of V0 minus dimension of V1. So this is the categorical dimension. And in particular, it can be negative. So even if if my field K is C, for example, it can be negative. So this is not the category of the same type. And in fact, over any field of characteristic not equal to, you can easily show that it's not of the previous type. And then you can generalize this thing. Namely, what you can do is you can take a G, which is a supergroup scheme, and this simply means that you take this means that you have some Hopf algebra H equals O of G, which is a supercommutative algebra. So this simply means that, again, it has a decomposition like this, H0 plus H1. And then you have A times B equals to minus 1 to the degree of A times degree of B, BA, where A and B are homogeneous. And it has to be a Hopf algebra in an appropriate sense. So, for example, cohomology of a topological space, which is an H space, will be such a supercommutative Hopf algebra. And then basically you can take a representation category of this G, except that to get the most general case, you need to make a tiny modification. Namely, you have to fix an element that is going to define parity. So you take G in G of K. So this is a points of K. So this is just home from this H to K as algebras. and it should have square 1. And conjugation by G on functions on G should be the parity transformation. So it acts by 1 on H0 and by -1 on H1. And then we can take the category C equals to rep of G G. So representations of this G on superspaces such that little g acts by parity. So an example of such a thing is of a supergroup scheme, which some people may be familiar with, is GLMN, the group of general linear group of a vector, supervector space with m even vectors and n odd vectors. And in this case, we can take this little g to be 1, 1, 1, 1, -1, -1, -1. So this is for the even vectors, and this is for the odd vectors. So we can ask whether, by the way, we went from the groups to these categories by forgetting both groups and vectors, and one might ask whether we forgot the group or supergroup. And the answer is no. So actually it remembers about the group. And so for example, if we start with an ordinary group scheme, not a supergroup scheme, G, so if G is the usual group scheme, affine group scheme, and C is the category of representations of G, then how do you reconstruct? How to reconstruct C from G? And you can do this in the theory which allows you to do it, called Tanakian reconstruction. So what you do is you look at monoidal functors.
G from C or C from G?
G from C, yeah, thank you. So you look at symmetric tensor functors from C to the category of vector spaces over K. So if you have a representation category of G, there is an obvious such functor, which is the forgetful functor. And its properties are that it's a functor that preserves all the structures, preserves the additive structure, preserves the tensor structure, and preserves the symmetric structure. So this is called a fiber functor. This notation, this terminology comes from topology, because in topology, representations of a group comes as a local systems on the classifying space of this group. And in this case, this is a functor. If you have a local system, a locally constant sheaf, you just take the fiber of this sheaf at that point. Although this functor is forgetful, it actually remembers everything about the group. So we can reconstruct this group simply as the group of automorphisms of this functor, which preserves the tensor structure of this functor. The group of isomorphisms of f onto itself as a tensor functor. So one can write down the axioms for this, which I will not do. So you can reconstruct it in this way. And there is a similar, so such categories are called Tanakian. Such categories which have such a functor. And I should say that this functor is unique. So if I just give you the category, then there is a theorem that f is unique. It's the unique functor that preserves all the structures. And you can reconstruct the group as automorphisms of this functor. And the categories that have F, that have such F, then necessarily unique one, are called Tanakian. And there is a similar story in the super case. There is a similar story in the super case, which where you have in the super case you have a functor from C, but in this case to the supervector spaces. Again, in the case when you have that, it is just forgetful functor, and again it is unique, subject to condition that it preserves all the structures. So it's a unique fiber functor, which means symmetric tensor functor. And we can reconstruct this G as automorphisms of F. And you can reconstruct the parity element also. It just acts by parity on every space here. So here you have to be a bit more careful, because this group is in the category. It should be internally in the category of supervector spaces. But this is a minor point, and essentially it is the same story. And such a category is called super-Tanakian. And so so you might, and by the way, when characteristic of k equals 2, then there is nothing new here, because minus 1 equals 1, and so Tanakian and super Tanakian is the same. But otherwise, it is not. And super Tanakian is a generalization of Tanakian. So so the question is, are there more general categories? And so why do we care about this question? Well, because if you have a symmetric tensor category, it's a natural place where you can do things like commutative algebra. When you have a commutative algebra, you study ideals in it and so on. You can do algebraic geometry if you think geometrically about the spectrum of this algebra. Or you can do Lie theory when you think about Lie algebras, Lie groups, algebraic groups in this category. And if this category is Tanakian, which means it's representations of some G, this just means that this geometry that you would be doing is just geometry, equivariant geometry. So geometry with the action of this group. And if it is super Tanakian, this means that it would be equivariant supergeometry, which means supergeometry with the action of the supergroup. So in some sense, you will not have anything new if you consider geometry in these categories. So that's the question. That's why we have the question, are there other categories? Because if we discover some new categories which are not of this type, we will discover some new type of algebra and algebraic geometry. And so the question is again, are there other categories? Symmetric tensor categories. And the answer is again yes. So let me show you an example in characteristic P. So I'm going to take now a ground field of characteristic P, where P is at least 5. Because for 2 and 3, this construction doesn't give anything new. So characteristic of K equals P, which is at least 5. And I'm going to start off with the category which I'm going to call C tilde. That's not my final result yet. It's just representations over this field of the group Z mod P. So this is the simplest group for which this category isn't semi-simple. It's easy to classify representations. This is given to us by the Jordan normal form theorem. So if you have the generator G, such that G to the P equals 1, then we can write this as G to the P minus 1 equals 0, but this is the same as G minus 1 to the P if we are in characteristic P. So this means that G minus 1 is nilpotent of degree of nilpotency P, and the representation is just an operator on a vector space whose pth power is 0. So such an operator by the Jordan normal form theorem is a direct sum of Jordan blocks of sizes 1, 2, 3 up to P. So indecomposable representations are J1, which is the trivial representation, up to JP, which is the P by P Jordan blocks. Well, of course, this category is definitely of the old type that we have discussed, but I'm going to modify it in such a way that it will not be. And so for this purpose, what we will do is we will take a quotient by negligible morphisms. So definition. Questions?
No. I want to see what negligible means.
Yeah, so a morphism f from x to y between representations is negligible if for any morphism in the other direction, gy to x, the trace of f composed with g is 0. So this definition actually was given by Grothendieck in the theory of motives, but it actually can be applied in this setting as well. And this is the notion of negligible morphisms, and they form a tensor ideal. So they form a tensor ideal. And this means that if you, first of all, they form, for negligible morphism from any x to any y, form a vector space. And also, if you compose a negligible morphism with any morphism on any side, or tensor a negligible morphism with any morphism on any side, you get a negligible morphism. And I will call this ideal n. And then, so we can consider the quotient category. C bar equals to C mod n. So this construction I will talk about more in the next lectures. And so what does this mean? It's a category where objects are the same as in C, but morphisms are morphisms in C modulo morphisms in n. And so what happens is, what happens when you do this? Well, you can describe explicitly these negligible morphisms. So actually this definition of negligible morphisms makes sense in any symmetric tensor category, because so the notion of trace makes sense in general. So you again do this thing, and then you apply. So if you have a morphism A from x to x, then you can apply A tensor 1. This goes to x tensor x star. Then you flip C x star cross x, and then to 1. And then the composition is a scalar, which is called the trace of A. In particular, trace of the identity is the dimension, as we already discussed. So this definition makes sense in any category. Here it is just the ordinary trace. And what do negligible morphisms mean? So there is a lemma. So this is an old story. This lemma goes back to Benson in the 80s, I believe. So that f is not negligible. So it is easier to say what it means for it not to be negligible. If and only if. So suppose x and y are indecomposable. In this case, it's easy to say what it means. F is an isomorphism, and dimension of x is not 0. Remember that in characteristic P, even for ordinary groups, we can have dimension equal 0 because dimension is the dimension mod P. So, so that's the characterization. And so therefore we can, what happens if you have an indecomposable object, its endomorphism algebra is local. And everything gets killed in the nil radical, and the unit also gets killed if the dimension is 0. So this means that we are forcing Schur's lemma. Endomorphisms of any indecomposable becomes just one-dimensional, except the case when it has dimension 0, when the endomorphisms is 0. So the object itself becomes 0. So this implies that the category C bar is semi-simple. It has Schur's lemma. Home from x to y between indecomposables is one-dimensional if x is isomorphic to y, and 0 if x is not isomorphic to y. And simple objects are indecomposables in C of dimension non-zero. So therefore, in our example, it would be L1 through LP minus 1. And these are obtained from J1 and JP minus 1 by this bar procedure. But the JP1 gets killed because it is the P by P matrix and its dimension is 0. So we've got this thing here. And then one can compute the tensor product of these things. So how do they tensor? So if you take Lm tensor Ln, this is the direct sum from I equals 1 to the minimum of m n p minus m p minus n of L let me just write it. M minus n plus 2i minus 1. So this should remind you the Clebschgordan rule of tensoring representations of SL2. If you didn't have p minus m and p minus n, that would be exactly that. And that's simply because when we tensor Jordan blocks over complex numbers, they tensor in the same way as representations of SL2, simply because the element E of SL2 acts on an irreducible representation just by the Jordan block. But in characteristic P, after this semi-simplification procedure, this is how they tensor. And in particular, what we see from this is that if you look at, so this category C bar, then if we take P equal 2, we will just have one object, so this will be just the category of vector spaces, nothing new. If P equal 2. Now, if P equals 3, we will have two objects, and it's easy to check that we will get super vector spaces. Actually, it's an enjoyable calculation. How do you get that sign out? So, supervec K, if P equals 3. But when P equals 5, let us try to multiply what we get here. So let's take L, so L1 is just 1. So let us multiply L3 by L3. So in the usual Clebschgordan rule, that would be L1, which is 1, plus L3, plus L5. But in our case, there is no L5 because L5 is 0 in characteristic 5. So you get this rule. And therefore, if you have dimension of L3 equal x, then you will get the equation x squared equals to 1 plus x. So of course this equation has a perfectly nice solution in characteristic 5, namely 3, but it doesn't have a solution in integers, because solution is a golden ratio. So that means that this category can't possibly have a tensor functor to vector spaces or to supervector spaces, because such a functor has to preserve dimensions in the usual sense, and that's impossible because the dimension of this would be an irrational number. So that's why we have to do representation theory without vector spaces. If you want to do modular representation theory, this operation of modding out representations of whose dimension is divisible by p is quite common, and you end up with a tensor category which cannot be realized in vector spaces. So that's another example. And so let me conclude with the theorem. So, I raise again the question, are there others? Well, what about characteristic 0? What about C? Because we were in positive characteristics. So the question is, can we do anything over C? And the answer is, are there others? And the answer is only very big ones. So so there is a theorem of Deligne. I will end with formulating this theorem, which basically says that now only very big ones. So the very big ones are very interesting. They are called Deligne categories, and I'll talk about them tomorrow. But what does Deligne theorem say? Well, it says the following. So we say that C has moderate growth if for every object x in C, there exists a constant Cx greater or equal to 1, such that length, we said that everything has finite length. If you raise x to the nth power, this is at most Cx to the n. And it's clear that any representation category of a group or a supergroup has to satisfy this condition, because you can simply take Cx to be the usual linear algebra dimension of x. But it turns out that there exist categories that violate this condition. They are called Deligne categories, and we will discuss them tomorrow. But if you impose this condition, then you get a remarkable theorem of Deligne in 2002, which said that every symmetric tensor category over a field of characteristic 0, let's say C, which is of moderate growth, is a super Tanakian, which means that there exists a fiber functor from C to supervec K, and C is representations of some supergroup. So we don't get anything new compared to what I told you about if we impose this moderate growth condition. So what I'll talk about in the next lecture, first of all, I'll talk about the categories that violate this condition. So that's a very interesting categories, which are basically interpolations. So one of the prominent examples is interpolation of general linear group GLN to the case when n is an arbitrary complex number, not an integer. But and also I'll talk about what happens in characteristic P. Even if you impose this condition, you still get those examples. So what could be the situation there? And the situation there we still don't understand, but I will tell you what we do understand and how it's related to modular representation theory. And that would be the third lecture. Okay, thank you very much.
Okay, questions?
I have a question that's only tangentially related, maybe. I never understood why you only look at Z2 graded things and not ZN graded things or
Well, I mean, so we have to have a sign rule. So it has to be symmetric. So when you switch two things, it has to be -1 to some power. So if you have ZP, then it is more natural to say that when you switch, you multiply by a root of unity. But that would not be symmetric, because if you do it twice, you don't get the identity. So that's a braided category. It's interesting, but you cannot do really algebraic geometry and commutative algebra in those. Well, there is a notion of commutative algebra, but it's not. I mean, it's much more. It's very interesting. Actually, commutative algebras and braided categories are very important, but they don't. But they're like quantum group, more like quantum groups. So it's not. It's not. Here we're trying to generalize ordinary group representations.
Other questions? Let's thank Pavel again.